Let's begin. Hi, everyone. This is the last lecture I will give you this semester. And as promised, if I'm able to get back, I will attempt to do so to the best I can. And wish me all the best. Next week is a very important one. Your thoughts and prayers will be helpful. For your final exam, like I said last time, you will have a handwritten part and a part that you have to deal with online. So if you go on your Canvas assignments, there's final exam, handwritten part, final exam, Canvas questions. For those who are in class, coming in person, you will be given the handwritten parts. So you'll just work through those in the class. You don't have to upload anything. You'll give the sheets back to Michael. However, you will have to do the Canvas questions, which is on Canvas online, multiple choice, etc. So you'll do both. For those who are remote, you will have to upload your solutions, take pictures, put a PDF, and then upload for the handwritten part of the exam. Like I said, also you will be given a full equation sheet. I suggest you become very familiar with that sheet to find your way around because you will use it 100%. And so that's a guarantee. So make sure you're familiar with that. You can print your own copy. It will not count toward your cheat sheet, but we will give you a copy. So I'm sending those off to the press today, so we get everything printed out. And I'll show you an example today of how you will be using that equation sheet. Essentially to put down the relevant set of equations that you need to use. Now, today's lecture will not be very long because I will just show you one or two examples of exact solutions to Navier-Stokes. Then Maher will continue next week. He will repeat the ones I did, but he will be in class with you in person. It's a different interaction. So he will repeat those examples and continue through the remaining examples. There's about six of them on the slides. And as I said last time, they are also replicated on my YouTube channel, and I already put those links on the main Canvas page. Okay, so anything I missed, any things that were not clear, please email me, copy Michael. And as you go forward, when you repeat these examples at home, make sure if you have questions, you copy Maher as well. He is added on Canvas. You'll see his name on Canvas, Maher. He'll introduce himself next week as well. So copy him because he will be able to also answer the fluids questions. Not that Michael can, but he's focused more on other things. And Maher took fluids with me, so he knows how I teach and I approach fluid mechanics. So he will follow that same nomenclature and that same strategy. Okay? Any other concerns, comments? Let me know. This is probably the last day you'll have access to me. And hopefully when I'm back on my feet, I can re-engage with you sooner than later, God willing. Okay, so without any further ado, let's start the last chapter. There were so many other things I wanted to cover, but I think this is going to be to get you, we've already gotten further than anyone anticipated I will cover in this course, including myself. And so I'm very happy that I was able to get you here, because what I will teach you is a really cool way of solving some Navier-Stokes problems. So the Navier-Stokes equations, which we saw last time, they're the special case of the Cauchy equations, and especially for the gas. So with the Cauchy equations, the equations of motion are in terms of the stress or diffusion tensor. Once you specify that tensor, You're specifying whether you're dealing with a Newtonian, non-Newtonian fluid, with a solid even. Doesn't matter as long as you give the formula for that stress tensor. Now, in continuum mechanics, we call these constitutive models. So in continuum mechanics, these stress tensors, they're not symmetric. They depend on history of the material, etc. They're way more complicated than the ones we deal with in fluids. And in fluids, once you focus on the Newtonian stress tensor, you get the gas dynamics equations. They're general, laminar, compressible, incompressible, turbulent. They do it all. But then you do certain simplifications on those equations, and then you get a bunch of other equations, like I mentioned last time, irrotational flow, Euler equations for inviscid flow. When you put specifically constant density, constant viscosity, and you simplify, you get the Navier-Stokes equations. And those are the equations we will be dealing with for the rest of the semester, and the solutions to those equations. Now, the purpose of any analytical, any approach to either further simplify the Navier-Stokes equations or to solve them analytically is to be able to develop simplified ways of visualizing what these equations are doing. So can we solve these equations in general? No, we cannot. They're complicated. Analytically, no, we cannot. They're complicated. In very special cases, we can solve the 3D version of them, but those are like unrealistic cases, not necessarily realistic, like a three-dimensional periodic domain, etc. So the only way we can solve them is numerically with computational fluid dynamics. But we're not going to do that in this course. Instead, we are going to take the Navier-Stokes, try to further simplify them, and see what we can do with those. Some simplifications will still result in simpler equations, but they're still nonlinear. For example, the boundary layer equations, you can convert them to a one-dimensional ODE, but it's like third order and it's nonlinear. So you have to use a numerical method to solve it. So that was Blasius's solution, Prandtl boundary layer, I don't know if you've heard of those words, but that's what's done there. Some other cases, you simplify the equations, but you can't further simplify them to get an analytical solution. You can't solve it analytically, so you still have to do a numerical method, but it's an easier numerical method, right? So you're doing maybe an ODE int or a couple of ODE ints, etc. It's not that complicated compared to the full system of equations. On the flip side, there are even further simplifications for very specific types of problems where we can obtain an analytical solution. And the key word here is to reduce the equations, to find enough assumptions and simplifications that we can reduce the equations to a linear, to the linear parts only, to retain only the linear parts. And I'll talk about that in a second. This is going to be our working equation set. I'm showing this here in Cartesian coordinates, but we might also be dealing with a cylindrical case or a spherical case. So you'll just pick the equations from the equation sheet that was given to you. You have to choose which set of equations you're working with. If you are in Cartesian, you pick the setup the system of equations where you have Cartesian coordinates. If you are working with cylindrical, so flow in a pipe, which we will do. I think Maher will cover that with you. I don't think I will today. So in that case, you pick the cylindrical coordinates. If you're doing the flow over a sphere, you pick the spherical coordinates versions of these equations. If you are given equations with a stress tensor, I said non-Newtonian fluid, for example, you have to pick the equations that contain the stress tensor in them and do the substitution. Okay. The strategy that I will propose today is one way to find solutions for Navier-Stokes equations, and it's that strategy evolved over the years as I saw the types of problems we were solving. It's very simple, very useful, and very effective. It solves many problems. And obviously the problems that I will give you in the exam, and if there were any homework, I would give them to you so that you can simplify the equations in the way I'm going to explain. So here's the strategy. The strategy is, if we were to take the Navier-Stokes equations, but in tensor notation here, so I don't have three equations, just dealing with one equation. If we were the problem in these equations when trying to solve them, so let me get the annotator here. The problem from just a mechanistic perspective to solve this is this term, because it's a nonlinear term, and this term because it adds dimensionality in time and unsteadiness. It's not as bad as this guy from a solution perspective, but this guy is very complicated to solve. Now, when you look at this term is linear. In one dimension, for example, this would be simply uxx, okay? And if you assume that the pressure gradient is constant, or there's no pressure gradient but gravity is constant, then you have uxx equal to a constant, okay? And then you can very simply integrate twice and you get an analytical solution. So this is going to be the foundation of our strategy, is that we are going to look for enough assumptions to justify eliminating the unsteady term. So we're going to assume, oh, the flow is steady. What happens in the steady situation? Flow in a pipe, flow in a channel, flow between two concentric cylinders, the flow in a pipe with a cylinder being pulled out, the top cylinder is being pulled out, all at steady state. You can assume steady state, so you can knock out the transient term. If you assume also certain conditions on the u velocity, so for example, if the u velocity is only a function of one direction, so unidirectional flow, so flow in a pipe, for example, the velocity is only going to change in the radial direction, not in the axial direction. It's going to look the same in all axial directions. So with that assumption, you can knock out the advection term, which is the biggest, which is the harder term, and then you're only left with the diffusion term, which is linear, and either a constant pressure gradient or no pressure gradient, and or gravity. And with that, you can reduce the equation into something that looks like this. Literally, this is going to be our equation for all the problems that we will be solving. And then if you can further assume that the flow is unidirectional, so a flow in a channel, for example, the flow is only moving in one direction, the velocity is not changing from one position to another, it's only changing in the y direction. So your velocity is only going to be a function of the y direction, and then you can reduce this into one-dimensional problem and you can find the solution very easily. So that becomes clear as you work out more and more problems. There's no math magic here at all. It's a simple linear equation to integrate twice. The magic occurs in your ability to see the simplifications that you need to make, okay? And the key here is practice. So I will give you these 5-6 problems that cover pretty much all situations that we can see with this, and then I can vary these problems, change a pressure gradient, turn on gravity, turn off gravity. The mechanism is still the same. So if you practice these problems enough times that you can do them by heart, then you will be good to go and you will be guaranteed to ace the handwritten problems, okay? So we will start with an example as I explain my strategy. The first example is going to be the simplest type of flow, and that flow is going to be driven by geometry rather than gravity or pressure gradient. So I'm going to put I'm going to put water in a channel, and I'm going to put like a wooden piece or a conveyor belt at the top of that channel. So take a small channel and put a conveyor belt on it. I'm just going to move it at constant speed. So if you look here at the bottom of this channel, I have a fixed wall. So this is fixed. And at the top, I have a wall or a conveyor belt that is moving. Now, as that belt moves, it's going to drag the fluid with it. And our objective is to find what does that dragging looks like. Is the profile going to be linear? Is it going to be parabolic? What is it going to look like? That's what we are going to try to find out. And I'm giving you in the problem statement. So the problem statement usually will contain very clear things that you need to pay attention to. So consider the flow between two parallel plates. So when I'm specifying parallel plates, that immediately tells you there's no curvature. So this is probably going to be a Cartesian type flow problem with the top plate moving. So when the top plate is moving, this is going to tell me about what the boundary condition is going to be at that top plate. The fluid is incompressible, so check mark. So we are headed to the Navier-Stokes equations. and the flow can be approximated as one-dimensional. So in other words, I'm not worried about variation in the y or the z directions. So there's no v velocity component and there's no w velocity component. There you go. I told you, assume the flow is one-dimensional, so you can knock out the dimensionality for v and w. Viscosity is also constant. That nails it. So that tells us definitely we are dealing with the Navier-Stokes equations in Cartesian coordinates. The upper plate is moving at a constant speed u wall. So that's given to us. Find the velocity profile between the two plates. Okay, between the bottom plate and the top plate. Now, when I say velocity profile, what does this is the velocity. This is what we call a velocity profile. These arrows that you're seeing is that as we get closer to the bottom wall, what I know and what we will find in the end is that the velocity will be zero, and as we get closer to the top wall, the velocity is going to inherit the wall velocity. Okay, now what happens in between? Is it a straight line? Is it a little curve? We're going to have to find out. Okay. So the strategy has a few steps, and you have to follow these steps. In every problem that I'm covering here, I repeat those steps over and over and over again. And if you follow these steps, 1, 2, 3, etc., you will be guaranteed to be able to solve the problem. Eventually, you'll just jump to the solution because it becomes very clear. The first step is to start by sketching the geometry and getting a sense of what you expect the velocity to look like. So that first step, you don't have to sketch the velocity profile exactly, but you have to have a sense of what you want it, what you think it's going to look like. At this stage, you also want to know what is driving the flow. There are two things that will drive the flow: a moving boundary or a pressure gradient / gravity, or both. Okay, and so or you can have both, a moving boundary and gravity and a pressure gradient. Now in this case, I didn't mention anything about a pressure gradient. So most likely the flow is going to be driven purely by that top boundary, by that moving boundary. Okay. Now for the Couette flow problem, the liquid is between the two plates. The bottom plate is fixed, upper plate is moving at a constant speed, and the channel is otherwise open to the atmosphere. So think about this as a big channel, and I have a conveyor belt just like at one section. I'm trying to see what the velocity profile looks like in that section. The upper plate is driving the flow, and we're going to assume no pressure gradient. If I didn't give you anything about the pressure gradient, you should assume no pressure gradient. Okay. Now you can still solve it with a constant pressure gradient, which we will do later. If there's no pressure gradient, we expect the velocity profile to be linear, and I'll tell you why later, okay, at this solution. But even if you thought the velocity profile was not linear, so even if you came here and said, okay, this is my zero line, and at the bottom there's no, the wall is fixed, so the velocity is going to be zero. Even if you drew this, okay, that's still going to be okay. Okay, you're not going to lose points for this, because then the math will probably prove you wrong. Okay, it's going to prove you wrong. The math is going to prove you wrong. And you'll see why I expected this to be a linear profile. You see that later we will deduce that whenever there's a pressure gradient or gravity, the profiles will be parabolic. Okay. Otherwise, if there's no pressure gradients and no gravity, the profiles will be linear. Okay. So you do this first step, just get a sense of what the flow looks like. Okay, this is very important because it gives you a sense of intuition of what you're looking for. Okay, next step is to select an appropriate coordinate system. Flow between plates or a channel, then it's probably Cartesian is going to be best. Flow in a pipe, cylindrical is best. Flow over a bubble or sphere, then spherical is going to be best. So in this case, channel flow indicates that Cartesian is best. And this is the step where you might want to place your origin. Now, sometimes I will tell you put the origin at the lower left corner. You have to put it there. But in other cases, it's up to you. Some people might put the origin in the middle. Some might put it at the bottom. Some might put it at the top. It doesn't matter, okay? Because all of these solutions will be the same based on the coordinate system transformation, okay? So whatever coordinate system you choose an appropriate one and put the origin wherever you think it's convenient. Here, I could put it at the bottom, I could put it in the middle. There's not a major simplification to be obtained. So if I choose to put it in the middle, then my x-axis starts somewhere here in the channel. My y-axis is 0 at the middle. I have minus h over 2 at the bottom. and h over 2 at the top. Remember, the channel height was h. Okay, that was given to us. Okay, next, we're going to make reasonable simplifying assumptions about the problem. So you're going to ask yourself these questions. Is the flow steady? Yes, because I said consider steady flow between two channels. If not, you have to assume it's steady, otherwise you can't solve it, okay? Unless I tell you consider the unsteady flow, then you are going to assume steady, because otherwise it's very hard to solve. Is the fluid Newtonian? Yes, because I said consider Newtonian fluid, viscosity is constant. Is the density constant? Yes. Is the viscosity constant? Yes. I gave you that information. Is the flow laminar? Don't worry about that. We can only solve for laminar flows. Which velocity components are negligible? So in this case, I said the flow is unidirectional. So only the axial velocity component is non-zero. So U, the x component of velocity, is non-zero. V and W are going to be zero. Which pressure gradients are negligible? All of them are negligible. Okay, there's no pressure gradients anywhere in the flow. What about symmetry? Can we assume symmetry over here? No, we cannot assume symmetry. The symmetry assumption is only going to help you when you're sketching the velocity profile. Here, I cannot assume symmetry because the flow is totally asymmetric. Is gravity important? In this case, it's not. The channel is small. The gravity is not really pulling on the fluid. And I didn't tell you anything about gravity, so it's reasonable to assume there's no gravity. Okay, so the flow is incompressible, steady, all pressure gradients are zero, VW are zero, gravity is not important. Now, if gravity were important, it would be acting in the y direction, agreed? But then we said that the v velocity is zero, so then gravity would be only balanced by pressure in the y direction. It still wouldn't affect the axial velocity profile. Okay, it still would not affect the axial velocity profile. Okay, now apply your assumptions to the governing equation. So this is the key, the heart. I'm starting to sound like ChatGPT. Have you noticed recently you talk to ChatGPT? Oh, you're getting to the heart of the issue. This is a brilliant question. This is the core of the problem here. You're getting to the core of it, and it's so annoying and so patronizing, I find it. Yeah, I don't know if you've noticed that with ChatGPT. It's been getting incredibly more and more annoying. So I'm starting to sound like ChatGPT. Now we're getting to the core of the solution process, okay? Now what we're going to do, we're going to take the full equations, okay? And we're going to use our assumptions to simplify terms in the equations. The way others teach how to solve these problems is that you would do a momentum balance for each problem at a time, and then you deduce the equations from that. I'm going from a top-down perspective. The other approach is from the bottom up, where you start with the first principles. You do maybe a small infinitesimal control volume balance, and you derive the equations for that problem. What I'm telling you is that, well, we know that the Navier-Stokes equations govern this problem anyway. So why not start with those and then simplify them to find the equations for this specific problem? And that's what we're going to do. And I think this is much simpler than the other approach. So your objective, like I said, is to eliminate the nonlinear terms and the unsteady terms. Okay, so hopefully as you go through, you can reason your way to eliminate those terms. So let's see how this is going to work. And hopefully the simplified equations are going to be linear. So we have our continuity equation, div u equals 0, and we have the three momentum equations. So all of these together are Navier-Stokes for constant density incompressible flow in Cartesian coordinates. Now I'm going to start with continuity. Usually continuity, what it gives you a confirmation that the flow is unidirectional. Okay, so let's see how that works. So we know that V and W, let me show you this again. We know that V and W are 0. So if I knock out those terms, that tells me that du by dx must be 0, which confirms that the flow doesn't change, the velocity profile does not change as we go through the x position, as we go downstream. This implies that the velocity must be only a function of y. Now, I'm assuming unit depth, so no z direction. Normally, you would say the velocity is a function of y and z, but there's nothing going on in z. It's just a very, very thin channel. So assume unit depth. There's nothing going on in Z. So then you can assume that U is only changing in Y. And that's the profile we sketched. Okay, now we still don't know whether it's linear or it has a curvature to it, but we know it's only changing in the Y position. So the axial velocity, the velocity in the X direction, is changing in the Y direction. Okay, fluid mechanics is funny that way. Some people confuse this. Well, if it's the axial velocity, it should only change in the axial direction. No, that's not true. Remember, these velocities are fields. U is a function of x, y, z, v is a function of x, y, z, and w is a function of x, y, z, okay? In this case, the axial velocity is only a function of y, okay? And that confirms what we drew there. Now, we're gonna go after the momentum equations. We start with the x momentum. The flow is steady, so we knock out the unsteady term. Next, du by dx is 0, correct? That's from continuity. So we can knock out the first nonlinear term in the advection term. That was kind of one of the harder ones. Then v is 0, so we can knock out the second term. Then w is 0, we can knock out the third term. Yes, bingo, right? So we knock out the nonlinear advection term in x momentum. Next we go to the diffusion term. Okay, well, we said that du by dx is 0, so the second derivative of u with respect to x is going to also be 0, because du by dx is 0. So that's the benefit of doing the continuity equation first. Now, d2u by dy squared, I don't know if it's 0 or not. Agreed? Because we said u is a function of y. We know nothing about du by dy, and we know nothing about second derivative of u with respect to y. And remember when I said we're going to leave one diffusion term alive, and this is going to be this term, the second derivative of u with respect to y. So I'm going to leave that. Next, du by dz is 0 because u is only a function of y, so I can knock out the second derivative, the diffusion term in the z direction. And there's no pressure gradients, and there's no gravity. So my x momentum equation reduces to what? To a simple linear equation. Second derivative is equal to 0. Okay? So that's my x momentum equation. It's reduced to that. Now, you go to the y momentum equation without even saying anything. The y momentum equation is going to be 0, okay, or it's going to be balanced on its own terms because we said v is 0. So all the terms in the y momentum, all the terms in the z momentum equations are not going to matter to my solution because we want v and w to be 0. And so in that sense, the only equation that governs this problem, this Couette flow problem, is going to be this simple second derivative equal to 0. Now, because u is only a function of y, this turns into a total derivative, and it's just that very simple equation. Second derivative of u is equal to 0. Now, I want to connect this to why I expect the profile to be linear. So let's integrate this. Next, we want to integrate this. Okay, so before I integrate this, we need to, as we integrate these equations, we need to think about integration constants. So you leave the integration constants. To find the constants, you need to apply boundary conditions. There are two types of boundary conditions we will deal with. Walls, either fixed or moving walls, or fluid-fluid interfaces, all right? At walls, the fluid will always stick to the wall. So if the wall is moving, the fluid is gonna move at the same speed of the wall, correct? If the fluid sticks to a wall, to any wall, and if the wall is moving, it's gonna be dragged at the same speed. If the wall is not moving, then it's gonna be 0. We call that the no-slip boundary condition. Okay? If the wall is open or permeable, some flow might be coming in. So then you would have a normal component of velocity coming in. That becomes a little more complicated because that becomes a two-dimensional problem in that case. Okay? We're not going to cover that. At fluid-fluid interfaces, the velocities must be equal. U of fluid 1 or V of whatever velocity you're dealing with, of fluid 1 must be equal to the velocity of fluid 2. At that point, at the boundary, we will do a problem with fluid-fluid interface. But also the diffusive fluxes across that boundary need to be equal. So the diffusive flux of fluid 1 must be equal to the diffusive flux of fluid 2 at that boundary. Why is that important? Because that gives you, that relates the two viscosities of the two fluids. Remember, the diffusive flux is mu, comes from the stress tensor, is mu dui by dxj plus duj by dxi. So those need to be equal at the boundary, okay? And once we hit that problem, you'll see what that entails. And normally, if you're lucky enough, you're dealing with two fluids with vastly different viscosities, like water and air, okay? So the viscosity of air is about 5 orders of magnitude lower than the viscosity of water. And when you work out the formula, you get a ratio of viscosity of air over viscosity of water, and you can assume that that's equal to 0. So then in that case, you will assume that the slope at that liquid air interface is going to be 0. We will do a problem about that. That's going to be one of our last problems. I'll let Maher worry about this. But for now, we only have walls. The bottom wall is fixed. It's not moving. So the speed is 0 at the bottom wall. The top wall is moving. And so the velocity, the boundary condition at that top wall is going to inherit that speed. Now, before I apply boundary conditions, if you integrate this twice, you'll get u of y is equal c1y plus c2. And indeed, that confirms that the velocity profile is linear. Okay. Now remember, what did I say? I said if you don't have pressure gradients or gravity, the velocity profile is going to be linear. Now, if we had a pressure gradient or a gravity term, this would be second derivative equal to a constant. And you integrate that twice, is going to be a parabola. But if there's no pressure gradient or no gravity term, the right-hand side of this equation will always be 0. Because I knew we're going to have a diffusion term equal pressure gradient plus gravity. If pressure gradient and gravity are 0, then you have a second derivative equal to 0. The solution is a straight line. So indeed, if you drew the profile as parabolic, this should fix that for you. Okay? The flow is going to be linear in this case. Okay? Now you apply the boundary conditions. You say no slip at the bottom wall and no slip at the top wall. So no slip at the bottom wall means that the velocity at minus h over 2 is, you apply the formula, you put minus h over 2 over here, that's equal to 0, okay, because there's the wall at the bottom is not moving. No slip at the top wall, so at h over 2, u at h over 2 needs to be equal to u wall, okay? So now we have two equations and two unknowns with C1 and C2, and you simply solve for C1 and C2, like just normally do, and you get C1 equal U wall over H, and C1, sorry, let me fix this. C1 equal U wall over H, and C2, you'll get that equal to U wall over 2. Okay, and then finally your velocity profile is indeed a straight line profile. It's U wall over HY plus U wall over 2. Okay, now you need to do a sanity check here. You need to make sure that your boundary conditions are satisfied. So now you come to the solution and say, excuse me, at minus h over 2, do I get 0? If you plug here, instead of y, you put minus h over 2, you're going to get minus u wall over 2 plus u wall over 2. That's going to give you 0. Indeed, we satisfy the bottom wall boundary condition. At the top wall, y is equal to h over 2. You're going to get u wall over 2 plus u wall over 2, which is equal to u wall. Indeed, at least you satisfy your boundary conditions. Okay, that's a sanity check that you need to do immediately after you find your integration constants and you solve for the problem. Now we have an analytical velocity profile for this Couette flow problem. It's really cool. Once you have the analytical formula, you can plot it and you can ask a few things about it. You can ask, for example, what is the flow rate across the channel? What is the average velocity in the channel? And what is, for example, the diffusive flux or the shear stress at the walls? Okay, because that's gonna induce a force. For example, you might ask, how much force do I need to apply at the top of the channel to move this flow? Okay, we'll do a couple of things here. I'm going to compute the volumetric flow rate. So the volume flow rate is essentially the integral of the velocity profile at any cross section in the channel or the pipe. So if you were to take a cross section from minus h over 2 to h over 2 and you integrate the velocity profile, you're going to get the volumetric flow rate. So in this case, this would be integral from minus h over 2 to h over 2 uy dA. Now, the area here, I have unit depth, so my area is simply dy. My unit area is dy times 1. All right, and then you integrate this, and you can do this analytically, and in your exam, you should use your fancy calculators. That's totally allowed to do these integrals. Please do that, because you're going to have much more complex integrals that you need to solve, that I will ask you to solve. So do that with your calculator, please. Okay, and then when you do this, you get the volumetric flow rate u wall over 2 times h, and it's constant. It should be constant. The flow is incompressible. Okay, the flow rate, the volume flow rate at any cross section needs to be equal to the flow rate at any other cross section. You can also calculate what we call the average velocity. So if you were to think that on average, what is the velocity at any cross section, you simply take that flow rate and divide by the area. So in other words, if the flow was only uniform, okay, if the flow was uniform, velocity is constant everywhere along y, what would that velocity be? You simply take the flow rate and divide it by the area, and that gives you what we call the mean velocity, and in this case, it's u wall over 2. That makes sense. The profile is linear. It's 0 at the bottom. It's u wall at h, at the top wall. Then the average is going to be u wall over 2. Okay, and with that, you solve your first Navier-Stokes fluid problem. Okay, it's really that easy. Don't overcomplicate it, because I'm not gonna overcomplicate it for you. If you see any overcomplication, it's only gonna be in your head. You always need to recover a diffusion term equal to either 0 or a pressure gradient or gravity, or gradient, pressure gradient and gravity, with or without moving walls. That's what you need to aim for in all of these problems. There's no other way we can solve these problems with this strategy unless you convert everything to this form, okay? Unless you convert everything to this form. All right, now it's time to ask whether the solution makes sense. You can, re-examine your solution. You can plot it. You can compare to some experimental data, so that becomes more of a project type question. But at least do your sanity checks. You check your boundary conditions if they are satisfied, and so on. Okay? Do you have any questions before I move on? Well, you're not the speaking crowd, so I'll let your questions over Canvas. And that's okay. Sometimes you need to go back and review what's been done, right? So you start asking questions, but you have to. So the practice that you needed to do on deriving the Navier-Stokes equations, that's on you. There's no homework assignment for that, but it's on you to review and do things by hand. Okay, same here. These problems, you go look at the problem statement and solve it from scratch on a piece of paper. No ChatGPT, no nothing. It's you, your pen and paper, and possibly a calculator to do the integrals. Okay, you can plot in Python too if you want. Okay, so I already kind of mentioned this. When seeking this analytical solution procedure, you will have to simplify everything to obtain a diffusion term equal either 0 or pressure gradient or gravity or a combination of those, plus boundary conditions. Okay, boundary conditions, you're going to either have moving walls or stationary walls or a liquid interface. Okay, the boundary conditions help with the integration constants, and with the integration, with the diffusion equation, if the right hand side is 0, you have a linear profile. If it's not 0, it's going to be parabolic. There's no other mechanism, there's no other solution for any of this. Okay, now the type of flow we looked at is a geometry driven flow. It's a boundary that's moving the flow. We had no pressure gradient, no gravity, no nothing. Okay, and that's called a Couette type flow problem. The Couette flow problem could be two spinning disks, okay, a stationary disk and a disk that's spinning on top of it. Or I could have two pipes and the interior pipe is being pulled out, or the exterior pipe is being pulled out, or they being pulled in different opposite directions. Okay, that is going to all to be a Couette type flow if the pressure gradient and gravity are 0. If the pressure gradient and gravity are not zero, we're going to call that a Poiseuille type problem. Okay, so the classic flow in a pipe with a constant pressure gradient or being driven by gravity, that is going to be a Poiseuille type flow problem. And it's going to result in a parabolic profile because the right hand side of the diffusion equation is not zero, of the diffusion equation that we simplify to. Now you can combine both. I can take that Couette flow problem and throw in a pressure gradient. What are you gonna get? You're gonna get a parabolic profile. It's gonna look interesting. It's a parabolic profile, but the top boundary is moving as well. Okay, so it's gonna look like a weird parabolic profile, but it will work and it can work. All the problems that you're gonna see in this setup are either gonna be Couette, Poiseuille, or combination. And I can do this in all sorts of coordinates, in all sorts of setups to try to confuse you. But you're strong. You're not going to be confused because I told you so. In the end, it's either going to be Couette, Poiseuille, or a combination of both. And that's it. Anything that takes you away from this, you are complicating the solution. So you need to make the assumption that will make you uncomplicate the solution. Okay? Let's do the next problem. We're going to stay in Cartesian coordinates, and that's going to be Poiseuille flow in a channel. Okay. In an exam problem, I'm not going to tell you it's a Poiseuille problem. I'm going to tell you, hey, assume pressure gradient is constant or gravity is constant. You, in your mind, you should immediately deduce that this is a Poiseuille type problem, and I expect a parabolic profile. If I tell you the boundary is moving, no pressure gradients, no gravity, it's a Couette type problem. Tell you boundary is moving, but there's also gravity, it's a combination Couette Poiseuille problem. Okay. Next, we're going to take those same two plates, but we are going to add a pressure gradient. So the flow is driven by a pressure gradient. So think of a pipe, and I have a lower pressure on the end of the pipe and a higher pressure on the beginning of the pipe. So that means that dP by dx is negative because P downstream is less than P upstream. And if it's constant, you have a constant pressure gradient across the entire pipe, that's completely legit. Then you have a constant value for the pressure gradient. You keep that in mind. So consider the flow between two fixed parallel plates. The fluid is incompressible and the flow can be approximated as one-dimensional. Viscosity is also constant. The flow is subject to a known fixed pressure gradient. Find the velocity profile. That's all I need to give you about this problem. Of course, I'll tell you the channel height is h, and you figure out what coordinates you need to do. So the first step is going to be, we need to sketch the velocity profile and sketch the geometry. So I'm going to put two plates here. Now, because I said there's a non-zero pressure gradient, I expect that the velocity profile is not going to be linear because I'm going to have a diffusion equation equal to a constant. To integrate that twice is going to be a parabolic profile. Now, how does the parabola look like? This flow, the plates are fixed. So none of the plates are moving. So it needs to be symmetric around the center line. So the parabola needs to peak around the center line, and you can draw the velocity profile like that. Okay. Now, furthermore, because the flow is symmetric, it cannot be linear. Because if it's symmetric, it has to be piecewise linear, and because the velocity is continuous, you cannot have a piecewise solution. It needs to be a continuous solution. So that also knocks out the idea of linearity. Okay, either way you approach this. We're gonna, because this is a channel, Cartesian coordinates are going to be best, and I'm also gonna place my origin at the center line. Okay, so, and I'm gonna assume the channel height is h, so y is equal h over 2 at the top and minus h over 2 at the bottom. Okay, that becomes clear. As you apply these assumptions over and over and over again, they become second nature to you. We're going to assume that the flow is steady, Newtonian, constant density, constant viscosity, so that we are able to solve it. Otherwise, we can't solve it. The flow is laminar, gravity is not important. We have a pressure gradient. It's symmetric around the center line, but that only helps us in drawing the velocity profile. Finally, you're getting to the heart of the issue, as ChatGPT says. Fiona is laughing because Don't you get that with ChatGPT? Isn't it so annoying? Oh, this is brilliant. You're getting to the heart of the issue. Anyway, okay. So now we come to the Navier-Stokes equations, and we have all our assumptions in compressible steady state. I have a typo here. All pressure gradients are not zero. Constant axial pressure gradient. My apologies, because that's. I promise ChatGPT did not generate these slides. I generated them, and because there's a mistake. Okay, let me just fix the constant pressure gradient thing. My apologies. Just give me one. Constant axial pressure gradient. Constant axial pressure gradient. Constant axial pressure gradient. Okay. Whew. Okay, we are ready now to start simplifying the governing equations. We start with continuity. We assume the flow is unidirectional, so V and W are zero. So that gives us the same mantra that du by dx is zero, and therefore u is only a function of y, because it's changing along the channel from the bottom to the top. Next, we attack the momentum equation, starting with x momentum. Flow is steady. Du by dt is equal to zero. First advection term, du by dx is zero. Second one, v is zero. Third advection term, w is zero. Now we jump on the diffusion term. Du by dx is zero, therefore second derivative with respect to x is zero. Now, second derivative with respect to y, we don't know. That's gonna be our dominant term, right? So we can't knock that out. But in the z direction, that's also zero, because u is only a function of y. What about the pressure gradient? Well, we said it's constant. So I cannot neglect that term. Or it might be a function of x, okay? But we said it's constant, okay? So we're not gonna knock that out. But gravity, there's no gravity. And therefore, now you see the difference between this equation and the previous problem. Now we have a non-zero right-hand side for the diffusion equation. Okay, it's uyy equal something times dp by dx, okay? And that's non-zero. The remaining equations are all zero because v and w are zero, or at worst, if there's a gravitational term, it will be balanced by pressure. It will not affect your primary direction, your primary velocity component, which is x momentum. We're done with this. Next, our governing equation is going to be this guy, and we can convert now to total derivatives because u is only a function of y, so this could be just a total derivative instead of a partial. And dp by dx is constant, is given to us as a constant. I'm still gonna keep it dp by dx, okay, but it's a constant. All right. Next, we integrate and apply our integration constants, our boundary conditions to get the integration constants. So now you can see that we will get a parabolic profile. I kept the partial derivatives over here, but you don't need to keep the partial derivatives. This gives you d2u by dy squared equal 1 over mu dp by dx. Density doesn't matter in this problem anymore. And then you solve this, you integrate twice, you get 1 over 2 mu, sorry, I have another typo here. Oh, good grief, all my typos. 1 over 2 mu. Well, thankfully you cannot deduct points for me, but I can deduct points for you in the exam, okay? All right, so I'll fix this. I'll double check. All right. So that you integrate twice, you get 1 over 2 mu dp by dxy squared plus c1y plus c0. And that's where you see that parabolic profile. So indeed, my intuition about the velocity profile was correct because I knew the solution actually ahead of time. No slip, now boundary conditions, no slip at the bottom plate. So u at y minus h over 2 is 0 because the bottom plate is not moving. No slip at the top plate, so the velocity at h over 2 is not moving, as 0. So I have these two conditions. You're gonna get two equations with two unknowns, c1 and c2, and you have to work those out. You can put them in your calculator symbolically, or you can eliminate them by like adding and subtracting the equations. So for example, if you add these two equations, you'll eliminate c1, so you can find c0. And if you subtract them, you'll eliminate c0, so you can compute c1, okay? So you can do both of those approaches to get c1 and c0. and then they turn out to be like this. C1 turns out to be 0, and C2 is minus 1 over 2 mu dp by dx h over 2 squared. Now, remember, dp by dx is constant, and it is also negative because the gradient is, the pressure is lower at the exit than at the entrance. If pressure gradient is positive, the velocity profile is going to flip. Okay? That's it. But it will still look like a parabola. All right? And then with this, you get this really neat formula. U of y is 1 over 2 mu dp by dx times y squared minus h squared over 4. So you can simplify the math. Probably have a typo here somewhere, but you get the idea. Okay, I get too excited once I get to the general solution. I'm like, I don't care about the integration constants. That's a mundane problem, right? But you should do it right. You should do it right to get the correct velocity profile. Okay, and that is indeed a parabolic velocity profile. It is symmetric at y at exactly y equals 0. And with that formula, you can get a bunch of properties. I will always ask you about the flow rate and the mean velocity. Or you will need to connect the flow rate to something else in certain problems, okay? So keep that in mind, that once you have the velocity, the analytical formula for the velocity profile, you can use it to compute the flow rate. And in this case, you can connect the flow rate to the pressure gradient. And now this was super important. When Poiseuille derived this solution, he derived it in a pipe because he was trying to study blood flow. And he was looking at the pressure in the vascular system. And with this formula, he was able to connect, if he can compute how much pressure gradient there is between 2 points on a vein, he could deduce the flow rate, the blood flow rate in that vein. That's incredible, right? Imagine your heart surgeon, oh, can you compute the flow rate for me between in the carotid artery? Like, so, you know, very useful stuff. Okay, the mean velocity is 2 over 3 of the maximum velocity. But what's the maximum velocity? Is the velocity at the center line, because the flow is symmetric. Okay, the flow is symmetric, so u at 0 is 1 over 2 mu, this formula h squared over 4. Okay, so I will do only these two problems. I'll let you go a little early, although I have like, what, 25 more minutes. But I'll let you go a little early, and Maher will redo these problems very quickly with you. I'll tell him today that I already did these, but he will go over them real quickly in his own way, in his own verbiage and explanation. But then next, he will cover Poiseuille flow in a pipe. So that gets us into cylindrical coordinates, and you'll see what happens in cylindrical coordinates. It is the same procedure, but now you have r, theta, and z, and typically your velocity is only going to be to change in the radial direction. So you only have a uz component changing in the radial direction. And you know, you'll see, we'll go through all the process, all the procedure, and then we have another problem where you have flow between two concentric cylinders that are stationary. So again, I'm adding more complexity to these problems. I can complicate them as much as I like, okay? And they're all solvable. Combined Poiseuille-Couette flow in a channel. So you have a moving wall and a pressure gradient, okay? Etc. And then what changes in these cases about, you can just look at this problem. This is a gravity-driven flow. When there's a conveyor belt moving a fluid, like cleaning in water, for example, there's a conveyor belt picking up stuff from the ocean, right? So that conveyor belt is a Couette flow type thing because it's a moving boundary, but gravity is also dragging the flow further down at an angle. What is this? This is a Couette-Poiseuille type flow problem, but there's a liquid-air interface boundary condition. And then you're going to have to figure out, you know, also from the equations, they all simplify. Look at that. They all simplify into a simple diffusion equation. You always need to uncomplicate your assumptions to get to a diffusion equation, whether equal to 0 or equal something. Okay, if there's pressure gradient, gravity is going to be equal to something, and it's going to be parabolic. That's it. Trust me, on all of these problems, whatever problem I throw at you in the final, I can complicate it, make it look very, very nasty like this. It will always simplify to a diffusion equation with either a constant on the right-hand side or 0. Always, always, always. Okay, don't overcomplicate things. So Maher will go through these problems with you. um, are there any more variation? Yeah, I can do 100 variations of these problems. Okay, but they will all reduce to the same idea: diffusion equation with either a constant or zero on the right hand side. That's it. Always, always, always. So my advice to you: don't get yourself entangled in webs like, oh, but the pressure gradient over here is a function of y. No, it's not. It's constant. Okay, it's constant unless I tell you otherwise. All right. So, but then once you have the analytical solution, you can do some really cool things, and Maher will guide you through this. You will be in very, very good hands. And I will let you go. I'm gonna miss you. I hope to still get to see you before the end, before the final exam, at least maybe once, maybe even over Zoom. If not, I will see you. I will see you around. Thank you, Isaac, for the message. Please keep me in your thoughts and prayers, and hopefully I'll be back. See you, and if after the exam, I'll see you around for your qualifying exams. Hopefully I'll sit on your committees if you're doing anything like related to computing or fluids, and I'll see you all succeed and do very well. I'm gonna hang out if you want to chat because I owe you this time, but otherwise if you need to leave and go start working on these derivations and these things, you're welcome to go. Thank you all. It's been a pleasure it's been an honor being your teacher this semester. I love teaching the first grad course. It's a critical path, and I hope you learned something.